Okay, here's a problem that is going to involve multiple conservation laws. So in this we see it says we have a new event for the proposed Winter Olympics, as seen below. We have this figure. There's an athlete will sprint 100 meters starting from rest, then leap onto a 20-kilogram bobsled. The person in the bobsled then slide down a 50-meter long ice-covered ramp. It's sloped at 20 degrees and into a spring, carefully calibrated to have a spring constant of 2,000 newtons per meter. The athlete who compresses the spring the furthest wins the gold medal. Lisa, whose mass is 40 kilograms, has been training for this event, and she can reach a maximum speed of 12 meters per second in her 100-meter dash. How far will Lisa compress the spring? Well, so we've got things that are moving, things that are changing height, and springs getting compressed. All that is solved typically with conservation of energy. That's going to be the easiest way. We're going to have kinetic energy of the bobsled and Lisa, then potential energy of gravitation because they're up on a hill, and that's going to convert into additional kinetic energy. Then they're going to hit the spring, and that's going to turn all that energy into the potential of gravitation. So if we look at the energy situation here, and you got a couple ways to do that with an LOL diagram, or I'm just going to do it with an equation right now. But if we take all the energies at position A, we'll say that this is position A right here. It'll equal, well, plus, and then we add to that any work done between A and B, any work of non-conservative forces that are not easily considered energies. That's going to be the same as all the energy at B, and B is down here where the spring is going to be compressed some, and the sled is going to be right squeezing it some distance x, right? We'll call that x. So what kind of energy do we have at the beginning? Well, Lisa's running, so we've got kinetic energy. We got kinetic energy at A. She jumps onto the sled. That's going to cause another little issue. Then she's elevated, so she's got potential energy of gravity. Not touching a spring there. No thermal energy or chemical energy, anything. No, nothing like that. Nothing is doing work either. So friction, if we had that, that might do work, but she's on ice. If we had some kind of engine, that might be work too, but we're taking just the velocity when she jumps onto the sled for that kinetic energy, and the sled's up in the air. So that's it. And that's going to equal, left a little space there, only kinds of energy we have at the beginning. Then that's going to equal all the energy at the end. But at the energy at the end, they're going to maximum compression of the spring, right? So to maximally compress it, you have to come to a stop. So no kinetic. It's going to be our lowest level. I'm going to call that the zero potential energy plane for gravitation. So no gravitational energy either. Only potential energy of the spring at the end. So kinetic and gravitational potential energy turns all into spring energy. Well, subbing in the equations for that, we know we've got 1/2 that kinetic energy. That's got to be, this is going to be the mass of the moving object, which is going to be Lisa and the sled. That's Lisa and the sled times their velocity at the beginning there squared. That's the kinetic energy. Plus m, again, this is the same mass, the mass of Lisa and the sled, g times their height, or delta y, whatever you want to call that y or that height. I'm going to make it a height, that they are above the zero potential plane. And that's going to equal 1/2 k, the spring constant, x squared, the amount that the spring is compressed. That's the equation for potential energy of a spring. So again, we have no kinetic on the right here at the end because maximum compression happens when the sled will stop and not progress any further. And we have no potential energy because I'm saying this is the zero height. This is HB equals 0. And this would be H at A, that height. So I'll have to figure those things out. So I've got to figure out what's this velocity, because it's not the 12. So she runs at 12. She's going 12 meters per second right here, but then she jumps onto the sled. That's a collision. That requires conservation of momentum. So this is after she jumps on, this velocity A. This height A is that height. It doesn't tell us. It does tell us it's 50 meters long. That's this length. That's 50 meters. And it's inclined at 20 degrees rather. So we can use some trigonometry to find that height. And the K they tell us. So I got to find that H, I got to find this V. So find V first. Let's find V. I'm going to do that over here. Find the velocity at A. Well, the momentum, all the momentums, it's a lowercase b, before the collision, is all the momentums after the collision in the x direction. Momentum is a vector, so we have to worry about direction in that case. Energy is not a vector, so it's a scalar quantity. Direction is not real important. So what do we got? We got the mass of Lisa, the velocity of Lisa. That's what's happening before. Then we got the mass of the sled, velocity of the sled, initial. Well, this is 0 because that sled's not moving. Then afterwards, they stick together. The mass of Lisa plus the mass of the sled times their velocity at what I call A, velocity at A. So we can plug those numbers in. Lisa's, what's her mass there? 40 kilograms. 40 kilograms times her speed of 12 meters per second is going to equal the 40 plus the 20 times VA. So working that out, do a little algebra, you get that VA, I need to pan down a little bit so you can see it. Doing that math, right? 40 times 12 divided by the 60 is 8. VA is 8 meters per second. All right, I've got that VA. I've got the mass. That mass is the 60. What is that height? Well, let's solve that over here. That height at A, well, that's the opposite side of this triangle. So it's equal to the hypotenuse times the sine. So it's going to be equal to 50 times sine of 20 degrees. That's the height of A. So 50 times sine of 20, make sure you're in degree mode. 17.1. 17.101 is height of A. That's enough digits for us to keep. So, all right, we got to find this x. So I'm gonna do a little bit of algebra there and then sub everything in. So I'm gonna multiply everything by 2 and divide everything by k on that left. So I'm gonna get m VA squared plus 2mgha all over k. That's going to equal x squared. So my m is 60 because it's the mass of the sled and Lisa. My velocity was 8. That gets squared plus 2 times 60. G is 9.8, 9.81 if you want to be a little more specific. 17.101 is my height, and K is 2,000. Make sure you put this in your calculator correctly. looks like I did that right. Divided by 2,000. And I get 11.975, but that's x squared, right? That equals x squared. So x is the square root of that. So there's my work right there. I'll take the square root of that. Second square root of that. Enter. 3.46. So x, the compression of this spring, 3.46. Got inconsistent significant digits. It's like 2, looks like. So probably 3.5, but 3.46 meters is how far that spring was compressed. So a little conservation of energy problem that had a little conservation momentum included in it. Hopefully that's beneficial.